What is covalent bonding and how do we make molecules? Well, when compounds form between two nonmetals, electrons are not transferred from one element to another like we've seen in ionic compounds in our previous lesson, but instead the electrons are shared in order to give each atom a noble gas configuration. And we showed this in our previous lesson when we talked about the octet rule. We showed an example of a metal and a nonmetal where the electron was donated from the metal to the nonmetal, whereas in covalent bonding the electrons were shared. So this approach to bonding is known as the Lewis theory of bonding. So here we have the example of hydrogen. Hydrogen in our natural world comes as H2, meaning it has a bond between each of those hydrogens. So in order to make the bond, each hydrogen has one valence electron, and those valence electrons are then shared between the two hydrogens. And what we call that, when we share a pair of electrons, that is called covalent bonding. And the shared pair of electrons creates a covalent bond. So when I'm sharing an electron, I am creating a covalent bond in a covalent compound. If we are donating electrons, then it is an ionic compound creating an ionic bond. So let's pause to make sure we understand the difference between the two types of bonding that we have discussed. So in our previous lesson, we talked about ionic bonding. And ionic bonding was specifically between a metal and a nonmetal. And in ionic bonding, electrons are donated from the cation to the anion. So we're dealing with a difference in charges. And that's how we bind our atoms together. They're bound through electrostatic charges. Okay, we have a plus that's bound to a minus, just like magnets. So we have our cation that's bound to our anion. And we said we couldn't do this with two nonmetals because that would be a negative and they would repel each other. And the same with two metals. They would repel each other because they have the same charge. So ionic bonding only happens when we have an electrostatic attraction between a cation and an anion. Covalent bonding is our newest type of bonding, and this happens between two or more nonmetals. So we're looking only at the right side of our periodic table. Electrons are shared between each atom, and the shared electrons form a bond that holds the atoms together. And we can have multiple bonds in a covalent compound. So let's take a second and practice identifying the different types of compounds, because ionic compounds are between metals and nonmetals, and covalent compounds are between nonmetals and nonmetals. So you should take your periodic table out so that you can figure out where these atoms are to determine if they are metals or nonmetals and see if it's an ionic or a covalent compound. So our first example is CO. CO, and that O is capitalized. So we are dealing with carbon and oxygen. Now I'm not naming the entire compound, I'm just writing out what the elements are. We'll talk about how we name these later. But if I'm dealing with carbon and oxygen, if we look at our periodic table, both carbon and oxygen are both nonmetals. Therefore, this is a covalent compound. Our next example is calcium and fluorine. If we look to our periodic table, calcium is in group 2, so it is a metal, and fluorine is in group 7, which is a nonmetal. So, because this is a nonmetal with a metal, this is an ionic compound. What I want you to do now is pause the video and look at the last 4 examples that we have here on the screen. Determine what the name of each of those elements is, use your periodic table if you need to, and determine if it's an ionic or a covalent compound. In example C, we have Mg, which is magnesium, and we have oxygen. Magnesium is a metal, it's in group 2, and oxygen is a nonmetal. Therefore, this is an ionic compound. In our last 3 examples, we have chlorine, Cl2, so chlorine is just bound to chlorine. Since chlorine is found in the nonmetals, both of those chlorines are both nonmetals, so this would be a covalent compound. Next up, we have HF, hydrogen, and fluorine. Hydrogen, while it is found sometimes on the left side of the periodic table, it is treated as a nonmetal. It has very similar properties as the halogens. So hydrogen and fluorine are both halogens and both nonmetals, therefore this is a covalent compound. So let's write that note on the side about hydrogen. Hydrogen tends to be more of a nonmetal, mainly because it's a gas, and we can't have a metal that's a gas. Okay, and our last example is C2H6. So we have carbon and hydrogen. Yes, we have multiple of those atoms in there, but it's made up of both carbon and hydrogen. Hydrogen and carbon are both nonmetals, so this would be a covalent compound because hydrogen is a nonmetal. Okay, so now that we're able to identify the difference between covalent and ionic compounds, let's move on to how we address covalent bonding in our specific molecules. And some of this we've talked about in our previous chapter, but it's always good to review. So a molecule is a combination of at least 2 atoms in a specific arrangement held together by chemical forces called chemical bonds. A molecule may be an element or a compound. So we have diatomic molecules that contain 2 atoms and may either be heteronuclear or homonuclear. So homonuclear diatomics have the same nucleus. And when we have homonuclear diatomic molecules, we're typically talking about specific elements where it's more energetically favorable for them to exist as a diatomic molecule rather than as just a singular atom. And there are specific elements that do this. Those would be H2, N2, O2, F2, Cl2, and Br2. They prefer to be in diatomics just because it's more energetically favorable to share their electrons with another one of that atom. Okay, so those are our 6 elements that tend to be homonuclear diatomics. So that's when we say a molecule can be an element, that is what we are referring to. Heteronuclear diatomics mean they have 2 nuclei, but they are different nuclei. So this could be like carbon and oxygen for carbon monoxide, okay? We can also have polyatomic molecules, which are molecules that contain more than 2 atoms. So if it's 2 atoms, it's a diatomic. If it's more than 2, so 3 or more atoms in that molecule, it's a polyatomic molecule. Okay, so a chemical formula denotes the composition of the substance. And we've looked at those before in previous chapters as well as in our previous lesson in this chapter. A molecular formula shows the exact number of atoms in each element in a molecule, which we also have looked at in previous chapters. but let's review. So here we have H2O. In H2O, I have 2 atoms of hydrogen and 1 atom of oxygen. So from the molecular formula, I know exactly how many of each atom makes up that molecule. In NH3, I have 1 atom of nitrogen and 3 atoms of hydrogen. And finally, in HCl, I have 1 atom of hydrogen and 1 atom of chlorine. So our molecular formula shows exactly how many of each atom are in the molecule. The structural formula shows not only the elemental composition, but also how those individual atoms are arranged in the molecule and how their bonds are set up. So here I have a few structural formulas that we can use to find the molecular formula. So this would be considered one molecule of this compound, and that's what its structure looks like. So that's how the individual atoms are organized in that structure, okay, to create that compound. And we can use that to find the molecular formula. So we see that there are carbon in here. There's also oxygens in there. And there's also hydrogens in there. So we count how many there are. There's 1, 2 carbons. There's 1, 2 oxygens. And there's 1, 2, 3, 4 hydrogens. Now typically we would rearrange this so that hydrogen came after carbon, so this would be C2H4O2. That's just the typical way that we show this. We show carbon first, then hydrogen, and then everything else comes after that. Here's another structural formula that we can figure out the molecular formula from. Okay, so we have 1 sulfur, we have 2 hydrogens, and we have 4 oxygens. And remember, when we're looking at formulas, we do not need to show a 1 as a subscript. And then our final one over here is one that you may see sometimes in your textbook where we don't show what the elements are. Instead, we have this kind of ball and stick model where the red is oxygen and the white is hydrogen. So this would be H2O because there's 2 hydrogens and 1 oxygen, and that is obviously water. Okay. Our last type of formula to discuss is the empirical formula. So molecular substances can also be represented using empirical formulas, which is the simplest whole number ratio of elements. So let's add the word simplest. We've talked about simplifying our formulas in our previous chapter, so we're going to do that here as well with our empirical formulas. So, while our molecular formulas tell us the actual number of atoms in a molecule, so the true formula of a full molecule, the empirical formula gives us the simplified version of that formula. So it doesn't tell us exactly how many of those individual atoms are in the molecule, it just simplifies the formula for us. So for example, in a molecule of N2H4, there's 2 atoms of nitrogen and 4 atoms of hydrogen. I would need to know that that molecule has 2 atoms of nitrogen and 4 atoms of hydrogen. However, I can show this as an empirical formula and say, well, this can be simplified by dividing both of those subscripts by their common denominator of 2 and simplifying it to the empirical formula of NH2. The empirical formula does not tell us the actual number of atoms in the molecule. But oftentimes, the molecular formula and the empirical formula are the same, meaning the molecular formula can't be simplified any further. So there are times where the empirical formula does tell us the actual number of atoms in the molecule. So that's why I said it does not always tell us the actual number. So here's some examples of some empirical formulas compared to the molecular formulas. So first we have water. Water has a molecular formula of H2O. Since I can't simplify H2O any further, there's no common denominator between 1 and 2, then my empirical formula for water is also H2O. So here's an example where they are the same. Now we can't simplify it because even though we can take H2 and divide that by 2, I can't take 1 and divide it by 2 because that would give me HO.5. I can't have 0.5 of an atom. I can't have half of an oxygen atom. That's impossible because we think of them as whole values. So our ratios have to be whole numbers. So no decimals, no fractions, anything like that. Next up, we have hydrogen peroxide, which you may have in your medicine cabinet, which has a molecular formula of H2O2. The molecular formula can be simplified by dividing both of those subscripts by 2. So we get an empirical formula for hydrogen peroxide of HO. And you can see from the structure that we've essentially just canceled out 1/2 of that molecule because we divided both of these by a factor of 2. We have a few more examples of this throughout this chart, which you can look at on your own. But what I want to do is start to practice with these empirical formulas. Let's start simplifying some of these chemical formulas. So here we have the question, what is the empirical formula of C15H18O6? So what we have to do is determine if that can be simplified further by looking for the least common denominator between all 3 of these subscripts. So take a second and think of what number you can use to divide all 3 of those numbers by. It has to be the same number. What you do to one, you have to do to all of them. Okay? Think of what number you would use to divide those and simplify this formula. Now looking at this, some may say, oh, well, I can start off with 5 here, but I can't divide 18 and 6 by a factor of 5. That wouldn't give me a whole number. So 5 would not work. You could also think I'm going to divide it by 2 because I can simplify 18 and 6 by a factor of 2, but I can't simplify 15 by a factor of 2. That would not give me a whole number. Instead, we can try 3. That's the least common denominator for all 3 of those values. So if we divide all of those subscripts by 3, we get C5H6O2. And we know that that's our most simplified version because 5, 6, and 2 have no least common denominator amongst them besides 1. So that is our most simplified version. Okay, so let's look at a few more examples. Determine the empirical formula for each compound below. So take a second and look through these 4 examples and think of how you would simplify these, what you would divide everything by to get the most simplest version of that formula. If we look at our first example, we have C4H8N2O3. Now, if you think about it, we could try to divide all of these by 2, But I can't divide 3 by 2. That would not give me a whole number. There's no other number that we can use to divide all 4 of those values by, meaning this formula is our most simplified formula, and it is our empirical formula. So we would write the empirical formula as C4H8N2O3. What we can't do is say, well, I can divide these ones by 2 and simplify it to C2H4NO3. We can't do that because whatever you do to one of them, you have to do to all of them. So we can't divide 3 by 2, as that would not give us a whole number. So just because there's a least common denominator between some of those values, it does not mean that they can all be simplified by that value. If that was the case, then all of our formulas would just be CHN and O and CH and everything like that, because then they would all be divided by the same number of subscript that they have. So we can't do that. Whatever you do to one, you have to do to all. Let's look at our next one, P3N12. Okay, so I think we can all see that our least common denominator here is 3. We can divide both of those numbers by 3 and get PN4. Remember, if we have a subscript of 1, we don't show it. Okay, so we just leave it as is. Our next example is C12H22O12. Okay, we could try dividing all of these by 12, but we can't divide 22 by 12. That does not give me a whole number. So that's not possible. So let's erase that. So if we look at these numbers, we can see that they're all even, so we can try first simplifying by 2. So we would get C6H11O6. And we can see from there that I can't simplify 6, 11, and 6 any further. I can't take 6 and divide it here, because whatever I do to this one, I'd have to do that one. But that does not give me a whole number. So our empirical formula for that is then C6H11O6. In our last example, we have C8H18, and our least common denominator between those values is 2. So we get C4H9, which we can see cannot be simplified further because there's no common denominator between 4 and 9. Okay. So, as you can see from our practice here, that usually once we're getting down to those, prime odd numbers, we can't simplify any further. If we have a 1, then we can't simplify. If we have an odd number, we usually can't simplify unless it's by itself. Okay? So, we just need to start finding those trends in our least common denominators. Okay. A little bit more practice. Let's think about this. Which of the formulas below is not a valid molecular formula for the empirical formula CH2O? So let's see. We have CH2O as our empirical formula. We want to look at all of these possible molecular formulas and see if they simplify to that empirical formula. So let's start off with A. We have C2H4O2. So if I divide all of those by 2, I get CH2O. Check, that matches my empirical formula. Okay, what about B? C2H2O2. Let's divide all of those by 2, and that gives us an empirical formula of CHO. That does not match our empirical formula of CH2O. Next we have C3H6O3. We can divide all of those by 3, and that gives us CH2O. That matches. Perfect. We have C4H8O4. Hopefully we're seeing our trend here. We're going to divide by 4 and get CH2O. CH2O, which matches. And our last one is C12H24O12. So let's divide all of those by 12. They can all be divided by 12 to give CH2O. Check. So the formula that is not a valid molecular formula of CH2O is B. C2H2O2 is not a molecular formula of the empirical formula CH2O.